Welcome to Eugenius Panda Virtual Labs, where students and teachers access the virtual laboratory simulations for various science subjects. Hello, dear learners. Welcome to our video tutorial program. This video will explain the concept of valence shell electron pair repulsion theory and molecular geometry, or molecular shapes. It is a topic which is covered under Unit 4, the covalent bonding and molecular geometry, in Senior 4, according to Rwanda Education Board curriculum. Valence shell electron pair repulsion theory, that is what we have on the screen. Valence shell electron pair repulsion theory. And here we have the objectives of our video tutorial. At the end, you should be able to describe the valence shell electron pair repulsion theory. You should also be able to identify the molecular shape of a given molecule or ion. We have to be able to name the shape of a given molecule or ion. And finally, you should be able to state the bond angles or the bonding angle for a given molecule or ion. Let's start with the explanation of the concept. The theory has three postulates. First of all, it says that valence electrons, the electrons which are on the outermost shell around the central atom in a given molecule, they are the only ones involved in bonding. This also involves the surrounding atoms. If I have a molecule like this one, carbon with hydrogen, hydrogen, and another hydrogen atom, then only the valence electrons will be involved in bonding. Lone and bonding pairs of electrons on the central atom, they repel each other. Here we have bonding electron pairs only. But in a molecule like ammonia, we have bonding pairs and a lone pair. This is the lone pair I'm talking about. So lone and bonding pairs of electrons on the central atom, they repel each other. Remember, they are all formed by negative particles, the electrons. So there should be a repulsion because of the particles which have similar charges. In valence shell electron pair repulsion notation of a molecule, a bonding pair is represented by letter A, and a lone pair is represented by letter E. For example, in this molecule, methane molecule, we have 4 bonding pairs. So because there is no lone pair, the molecule is represented as AX4. But here we have 3 bonding pairs, 1, 2, and 3. So that is AX3, but there is also a lone pair. So we have E, AX3E. Lone pairs repel more than bonding pairs. This is because they are not experiencing an attraction between 2 nuclei. You can see the lone pair, which is here, it doesn't have a nucleus, which is attracting it from this side, the upper side. It is only being attracted from the nucleus of nitrogen. The descending order of repulsion is lone pair, lone pair. So the repulsion is strongest between a lone pair and a lone pair. And what follows is the repulsion between a lone pair and a bonding pair. And the weakest repulsion will be between 2 bonding pairs. So if you have two lone pairs, like here, they will be very far from each other to minimize repulsion. And the distance that will be between two will be greater, of course, compared to the distance which is between a lone pair and a bonding pair. And the distance between a bonding pair and a bonding pair will be the smallest, giving us a smallest angle, bonding angle. Lone pairs occupy large volumes than bonding pairs. Why is it like this? It's because bonding pairs are attracted by two nuclei, as I explained, and then they get stretched. It's like having a nucleus here and another nucleus here. And then the electron cloud will be stretched by the two nuclei, which are all or both attracting the electron cloud. But if you have a single nuclei here, then a lone pair will occupy a larger space because there is no other nucleus here to stretch it, to attract it and stretch it so that it can occupy a smaller space. Also, structures containing lone pairs have smaller bonding angles because of strong repulsion. When you have more lone pairs, the bonding angle between bond pairs will always reduce. The number of lone pairs increases and the bonding angle decreases. How do we predict the shape of a molecule? First of all, we have to draw a Lewis structure for the ion or the molecule. And secondly, you consider the shape based on the location of the nuclei in the molecule. The double bonds, you have to remember this, the double and the triple bonds, they always count as one shared pair, as a single bond. Locate the shared pairs and lone pairs on the central atom, and then you determine the shape based on the following chart. We have a chart here which explains everything. You have a linear shape if the molecule has this formula. This shows that you have two bonding pairs. You also have zero lone pair, and the bonding angle here will be 180. For example, if you have a tetrahedral shape for the orbitals AX4, there is a possibility of having all four electron pairs as bonding pairs with zero lone pair. In that case, the arrangement of electron domains will be the same as the shape of the molecule, and the bonding angle will be this one. There is also a possibility of having three bonding pairs with a single lone pair. In that case, the arrangement of electron domains will be different, or orbitals, it will be different from this shape. You can see here we have tetrahedral, but here it is trigonopyramidal. And we said when the number of lone pairs is increasing, the bonding angle decreases. You can follow the chart and determine, based on the number of bonding pairs you have and lone pairs you have, the shape of your molecule, the arrangement of electron domains, as well as the ideal bonding angle. How can we use the simulation to explain all this? Here we go. Here we have our molecule, which has a linear shape. Linear shape, why? Because we have a molecule or a model. Here we have a model with two bonds, two bonding pairs. You can tick here to know the name of the molecular geometry. And here you get the name of the electron geometry, arrangement of electron pairs, all of them. And if you want, you can deactivate that. What happens? If you want, you can add another bonding. When you add another bonding, now you can see we have what we call a trigonoplanar molecule. Trigonoplanar. Here we have the name. And even the electron domain geometry, it is trigonoplanar. Because, remember, this is because we have no lone pair. You can also add the fourth bonding pair. Now you can see the names have changed. We have a tetrahedral molecular geometry and tetrahedral electron geometry. Now let's remove one bonding pair and replace it with a lone pair. When you replace it with a lone pair, what happens? You can see now on the molecular geometry, we have a trigonopyramidal geometry, but the electron domain geometry remains tetrahedral. Because we have 4 electron pairs, the electron geometry doesn't change, but because when determining the molecular geometry, we consider the relative position of nuclei, and here there is no nucleus, so we consider this nucleus, this one, and the fourth, and we get a trigonopyramidal shape. What happens when we replace the second bonding pair with another lone pair? You can see the electron geometry doesn't change still. Why is it like this? It's because we have 4 electron domains. The arrangement still is tetrahedral. You can move this to observe it from different angles. But you can see the name of our molecule, the geometry of the molecule has changed. We have a bent molecule. You can see it's bent. Now, let's see how changing this, adding a lone pair, removing a bonding pair will affect the angles. So you can tick here to show the angles. You can see here we have an angle of 109.5. Let's check. First of all, let's remove the lone pairs and remove the lone pairs to remain with a linear molecule. The angle is 180. When we add the third lone pair, you can see in the trigonoplanar shape, the angle is 120. When you add the fourth, the angle changes, it reduces. So as the number of electron pairs increases, the bonding angle also decreases. Now let's check when we add lone pairs. On adding a lone pair, look, now it has changed. It is changing. It was supposed to be 180. Why? Because we have 2 electron pairs, 2 bonding pairs. But remember, this electron pair, the lone pair I mean, this one we have up here, it occupies a larger space and it creates a stronger repulsion. So that is the reason why the bonding angle here will be squeezed and reduced to 120 from 180. If I add a second lone pair, what happens? And see, the bonding angle still is decreasing. So as the number of electron pairs, specifically the lone pairs, increases, the bonding angle decreases. We can also use this button to remove everything, and we remain with the nucleus of the central atom. Now let's check when we use multiple bonds. I add 1, and I add another one. Still, it is the same as having a single bond here and a single bond here. The bonding angle doesn't change. And even the names, we have linear and linear. It is the same even when you use a triple bond. As we said, remember, multiple bonds are considered as single bonds. Now, let's go to some other shapes which have more than 5 electron pairs. Here we have 4. Now let me add the 5th. When you add the 5th, what happens? You can see now we have what we call a trigonal bipyramidal shape. The molecule we have here has a geometry which is called trigonal bipyramidal. And the trigonal bipyramidal is the same for the electron geometry. What happens when I remove this and add a lone pair? We get this. What we get will be something new, and the name also changes. We call this one a seesaw. It is the seesaw. But still, the arrangement of electron pairs, all of them, including the lone pair, it is still trigonal bipyramidal. You can remove another bonding pair and replace it with a lone pair. What we get is this. And see, it looks like a T. Okay, it looks like T. You can also see how the angles are changing. So we have a T shape, but still the arrangement of electron domains is still trigonal bipyramidal. And when you add another one and you remove one lone pair, what we get is called a linear shape. Linear shape with the bonding angle of 180. Okay, this is linear. It is also possible to have, you can also reset everything by using this button, and then we remove the 2 lone pairs and the second lone pair. Let me go to the real molecules. We get some examples of molecules. You see here we have a molecule of water. This is a molecule of water. What is the name of the geometry of our molecule? It's bent, you see? It's bent with 2 lone pairs and 2 bonding pairs. The geometry, what will be the geometry? It's tetrahedral because we have 4 electron pairs around the central atom. And you can also show the bond angles. You see the bond angles we have here. The bond angle is 1 or 4.5. It is too small compared to what we would expect in a tetrahedral shape. Why? Because of the 2 lone pairs which occupy a larger space. You can also use another molecule, like a molecule of CH4. You see what we have? Look, we have a tetrahedral molecule. That is the tetrahedral molecule with a bond angle of 1 or 9.5. Name of the molecular geometry and name of the electron domain geometry, they are the same. What happens when we go to something like ammonia? In ammonia, remember, we have 3 bonding pairs and a single lone pair. You can see the bonding angle has decreased, and the name of the molecular geometry has also changed. Trigonal pyramidal, but the electron domain arrangement is still the same. And still, you can reset everything. So this is what we can do with this simulation, and I hope you enjoyed everything. Hoping that you have understood what we have been explaining, let me remind you that we have a quiz. The quiz code is VID, we have it here, VID 001003. And how do you take the quiz? If it is your first time, here we have the steps. You go to the website, that is www.opanda.xyz. You click on login, it is here. And then after clicking on login, you click on take the quiz. It's there. And after that, you will get this interface. And in this space, you will type your invite code, the code I've shared. And then you click here to take your test. I hope you have enjoyed the video tutorial and you will be there for more videos. Thank you very much for always being with us.